Okay, so let us take one more sensor for automotive applications and try to sort of expand on the capabilities of this sensor. Today we will talk about LiDARs. LiDAR essentially expands to light detection and ranging, and it is based on a very simple principle. You are trying to estimate quite like radar. You are trying to estimate the distance between itself and some objects. You basically calculate the time taken by a pulse of light to travel to an object and back to the sensor. Very simple expression one can talk about is this distance calculation is, you know, the speed of light and you know the time it takes, and you know essentially if you divide by 2, assuming everything is you know, what should I say, symmetrical, indeed it is, at the rate at which you measure you can assume it to be symmetrical. You can easily calculate the distance between the object, which is the between itself, which is the LiDAR, and the object that of your interest. You can see that this LiDAR has become extremely popular in as a very important critical component in autonomous vehicles. Okay, and we will see why it is indeed the case, and how can one use this simple LiDAR system. Actually LiDAR is not a simple thing, but indeed the data that you get is quite straightforward, and interpreting it and saying that there is how it can be used for obstacle detection, for mapping purposes and all that is a very exciting area. Why has it become popular? That is the real question. It is not that LiDARs are you know, something that have appeared in the last 2 or 3 years or maybe half a decade. It is really not that, it is not the case. LiDARs have been around for more than 40-50 years. Okay, so it is not a recent technology. In fact, in several aeroplanes they install LiDARs, and it is used for mapping purposes. Only recently it has started becoming popular for automotive applications, particularly in autonomous driving scenarios, and it is extremely good for obstacle detection, and it is not based on camera, please note. So that is the good thing about LiDAR, because camera, if you put a camera, you know the problem. Lighting becomes an issue for camera. You must have good lighting. You should be able to differentiate between shades and an obstacle. For example, during summer you are driving on a highway and there are a lot of trees on either side. The tree shade of the tree falls on the road, and that could be regarded as something like a false alarm or like a obstacle if you are using a camera. Sometimes that same shade could have actually happened because of, often because of the there is an obstacle on the road. So in order to differentiate an obstacle from a regular shade object for a camera is extremely hard. Okay, this is something that LiDAR can actually solve, and quite reliably it is able to detect obstacles. Okay, so this is a reason why it has become very popular. And one of the companies which have pushed very hard with respect to LiDARs is indeed a company called Velodyne. Velodyne. If you look up its website, you will see there is it is a very popular LiDAR, and there are other companies which have also started coming now. Essentially this is a, you can imagine that it is essentially a laser source, multiple layers of laser sources. Okay, this is very important. You will not be actually in technical terms it is called multiple channels. Multi-channel LiDARs are what should actually be used in any autonomous or driver assisted modern technologies where sensors are used for obstacle detection. Even if you are doing augmented kind of driving where driver is there and several things are autonomous, even in the presence of the driver, then you will need sort of a multi-line. The reason is you will have to get a 3D image equivalent of a 3D image. Essentially a LiDAR will throw out a lot of points, and you need a 3D view of the whole thing in order to decipher indeed if it is a obstacle or otherwise. Okay, so that is the, so which essentially means you will have multi line, and if you look at Velodyne, you will get 16 line, you will get 32 line, and you will get 64 line also. Okay. You can imagine that if you have 64 lines of light data coming in, several parts, profiling becomes a lot more reliable. Take a very simple case. Okay. Imagine that the road is straight. Okay. Imagine that the road is straight and you have a nice vehicle which is moving forward. Now here all you need to know is if there is an obstacle on this road, right, there is an obstacle on the road, all you have to just look for scan all around, do a 360 degree scan. The light source, actually there is a motor, and that to that motor is applied this the light source is applied, is fixed, and then you are getting points all through the 360 degrees. If you are moving straight and you are scanning, you need only a single plane, 2D plane is sufficient, x and y is sufficient, you do not need anything related to z. But if the road is tilted, okay, and you are moving up here, you need a lot more information from here as well, because the obstacle may be just down here, and if there are no beams which are looking down below the road, you are not going to actually catch anything, right. Now you just imagine when the road is straight and the beams are, some of the beams are looking down, while they will be actually bouncing off the road when the road is straight, it is still okay, because you are, the beams are actually looking down, but the very first instant when the beam can actually bend and catch an obstacle and give you back information, you can quickly brake, which means either going up or going down. If beams are looking all through, you have the ability to take proper corrective action, something that even the humans cannot do, right. No camera can work, camera may, even if you have multiple camera systems, it may be able to do, but this LiDAR has the ability to catch an obstacle even though human eye cannot see the obstacle. That is a good thing. It is just not about that, the range of the LiDAR is quite amazing. Okay. You get ranges from 100 meters to about 300 meters. Okay. So the best of some things from Velodyne even can go up to 300 meters. Please look up the website, you will see. So you will have 16 line, 32 line and 64 line, just to take care of 3D mapping, plus 3D mapping ahead of 100 meters, ahead of 200 meters, ahead of 300 meters, which is a outstanding ability for the system to detect an obstacle, and it is available x, y as well as on the z plane. Okay. So before you actually want to go and do anything with the LiDAR, you should know several important things about the LiDAR. So let us typically look at some LiDAR which you can say is something that we regularly use in the lab, and that LiDAR specification I will put down just to give you a feel of what are all the parameters you should look out for before you actually buy a LiDAR. So first thing is the pulses, frequency of pulses. How often do you want frequency of pulses? So typically you can go anywhere from 50,000 pulses to about, I should put like this, right, about 200,000 pulses. Pulses what? Pulses per second. So you will get a humongous amount of data if you are working with LiDARs. And the second parameter is wavelength. What wavelength do you want the LiDAR to work? Typically if it is IR range, you are looking at 1500 to about 200 nanometer. Okay. This is used in certain applications, meteorology and all that. Then you can also have for terrestrial mapping, you can have a few, and so many other. So there are a full range of LiDARs for different applications, starting from 1500 nanometers, sorry, this is 2000 nanometers, 2000 nanometer, then you have 1040 nanometer to 1060 nanometer, then you will also get blue green lidars, blue green lidars typically go from 500 to 600 nanometer and so on. Okay. And you can also have ultraviolet lidars which are 250 nanometer and all that. So, you get a range. So, you should know what range of lidar are you looking for in your for your applications, and most of them are scanner based, right. So, that is a very important thing. So, now let us look at one lidar which we have in the lab. Okay. While it is really not mapping to this part, it is indeed in the IR range. Okay. It is a 905 nanometer infrared laser based lidar. Okay. This is the lidar that we are going to refer to. It is giving not at all at any high grade samples, it is just giving out at 500 samples. Okay. You are getting 500 samples per second, but you can typically go from 50,000 samples to 200,000 samples. Horizontal view is indeed 360 degrees, that means you are covering a nice 2D plane. Vertical view is very narrow, just 0.5 degrees. Okay. And since it is a rotating lidar, it has to be rotating in some either clockwise or anti-clockwise. So, rotation is counterclockwise or anti-clockwise. Okay. And then there are voltage requirements and all that. Motor can be rotating, spinning at 5 hertz. Okay. It is also rotating at 5 hertz per second. So, these are some typical settings that you may want to consider, and this is essentially the kind of lidar that we would like to demonstrate to you. So, let me now show you the actual lidar which is right here. It is rotating, as you can see, there is a nice rotating object, and that indeed is the lidar. It is being powered through some 5 volts or so, and it is placed on the same robotic platform system which we will be using all through in this course, essentially a platform called Kobuki which is housing this lidar. Okay. And there is, as you can see, there is a onboard computer, it is a Raspberry Pi hardware and it runs Ubuntu, and on top of Ubuntu runs this robot operating system, or also called the ROS, which is essentially an API for accessing several pieces of hardware for real time communication between hardware and the OS itself. And so the lidar here can work on ROS, right. They give you a ROS API with which you can actually talk to the lidar. So there is a nice API for ROS which you can use, and this lidar is called SCANS. Okay. So, and this lidar is not available anymore, for some reason they seem to have stopped it. So, we have a couple of them from which we have been experimenting, right. So, now let us see how do these points look when you capture them at this 5 hertz range. How exactly do these points look, and what sense can we make out from this basic lidar system. For that, let us now turn our attention to the monitor screen, and you can see this nice set of points. Okay. Now, you may be wondering what is the place, what is this, what are these set of densely grouped points, and opposite to that there are a set of 3 or 4 points which sometimes are 3, sometimes are 4, and why is it in that structure, right. You may be wondering what it could mean. It turns out, if you look carefully, let us look back at the lidar. Okay, let us look back at the lidar and let us see what exactly the LiDAR is viewing. To begin with, I must give you a quick disclaimer that this LiDAR is a 2D LiDAR. Okay, this is a 2D LiDAR. It is not looking at anything with respect to any height related information, which means if you go back to this LiDAR, you will see it is getting obstructed by this table, okay, and and exactly the table corresponds to the place where Nitesh and Sanmay are pointing their mouse. That must be the table, right. Now you may be wondering what are those points. Sometimes they are 3, sometimes they are 4. Again go back to the LiDAR and then you will see there is a chair there, right. So that chair essentially is creating those 3 points, it is creating those 3 points. Let us look at the screen again. The screen here shows these 3 points. So now you may wonder how did we arrive at that. Okay. We arrived at that because we think, actually we did a simple calculation to explain, to show you I would say the length of obstruction, call it the not length, I would say the width of obstruction. Let us say the width of obstruction width of obstruction in the table case is 163 centimeters. If you take the width of obstruction of the chair, okay, is 56 centimeters. Okay. So it is roughly 3 times, that means the length of the table is roughly 3 times. So if I have 3 points here, perhaps I should get 9 points here or maybe 10 points. If I get 4 points here, roughly 3 times means 12 points. So you should get something close to 12 points. So let us see what happens here, let us count them. So at this instant you get 3 or 4, let us take 3 because for sure there are 3, at least you should get 9 points. Can we go to the other side and count them? 1, 2, 3, 4, 5, 6, 7, 8, 9, right. So these 9 points essentially correspond to width of the obstruction. Why am I calling it obstruction? See, the thing is in LiDAR terms you have to be very careful what is an obstruction. Okay. Let us now zoom back on the LiDAR and take a little back so that we see where exactly is this LiDAR placed. The LiDAR is actually placed, this system is actually placed in between the chair and this table, right. If you assume that the LiDAR system is moving forward, it is not being obstructed either by this side or by that side. But if this system is moving in this direction, then it is moving towards the chair, and if it is moving in this direction, it is going to hit this table. So here is your trouble, you get a number of points, and now you have to decide what are those points which actually make sense for the LiDAR system. What are those points? What are the points that one has to consider to estimate the obstacle or otherwise. You are just interested in a binary answer, let us say, right, whether it is an obstacle or whether it is otherwise. So you can only estimate. to actually decide that something is an obstacle or not, it is insufficient to go by based on just the LiDAR data, I suppose. You may not be able to estimate it without other sensors. However, it is still possible because you know that this is a 360-degree LiDAR, and you know at what radial distance, for instance, these objects are actually located, which can actually cause a collision or otherwise. So, it is definitely possible, and you can use it, but typically LiDAR is not the only one that is used to decide on an obstacle. People actually fuse this LiDAR information with other type of sensors. It could be automotive radars and also sometimes camera, okay, and all of them to actually decide if it is indeed an obstacle or otherwise. So, this is the key takeaway from the fact that a LiDAR has a very good capability of detecting obstacles. Alright, so this is nicely shown in terms of number of points and the closeness and all that. Now let us see, we will try and occlude this LiDAR by coming close to it. Our Nitesh project staff will come closer. Now you can see he is coming closer, he is coming closer and closer, and he comes very close and stands there. Let us have a look at how the points change. Now you see there are lot of points in close proximity of the LiDAR, you can see a lot of points. Now I will ask him to put an obstacle in front of it and let us see what actually happens. He is about to place the obstacle, maybe the camera should show once, yeah, you see he has put an obstacle. Let us shift the camera back to the LiDAR points, you can see they are all grouped together, right. So you must make sense out of these points to say that this kind of grouping corresponds to an obstacle right in the front of the sensor, okay. So this is very important, and similarly if he goes away, moves away and moves steps back, let us say if he steps back, you get back the standard picture of the two obstacles which we started off with. So imagine that these points which are being displayed actually correspond to some angle, is not it, because you are doing a 360-degree turn, each one corresponds to some angle from which this point appears, and you actually know how far it is, not only just from angle but also you know roughly how far the obstacle is and at what angle the obstacle is, and this information, remember, will be coming to you in real time, particularly when you are driving an autonomous, when you are sitting inside an autonomous vehicle at extremely high speed, 100 kilometer or if not more, and decisions have to be taken by computers which are on board by just looking at these points, by analyzing the data from these points and taking real time actions, trying to avoid obstacles or trying to go around obstacles and successfully navigate to the destinations. So let us look at this object. Yeah, you see this object, it is a little dark color, it is black, almost black, and we will wrap this LiDAR around the we will use this surface, this black surface, and wrap it around the LiDAR. So let us see what happens. So Nitesh is now wrapping it around completely and he has closed it. You see that the points have vanished, several points have vanished because it is almost wrapped to 270 degrees. Clear indicator in a little more, can you wrap it a little more, wrap it as much as, yes, okay. Let us see the number of points, you can see the very few points, you can count them on your fingertips, 3, 4 points, 5 points perhaps, and if you remove it and move away you will get back all the points and a nice good picture, which is a clear indicator that black is something that cannot reflect back, is not it, it is a black body, and therefore no light can come back in any of the electromagnetic spectrum if it actually hits a black object. And therefore, one of the biggest problems with LiDAR is if it is a dark object, black object, the number of points that you get back are so small that you cannot make out anything from the objects which are in front of the LiDAR. Therefore, you will carry that risk of missing an obstacle if indeed this LiDAR is used. So, every sensor, every technology has its own limitations, and this is one such limitation. But do not have to worry so much about it. You know that if you put 16 line or 32 line or 64 line, at the same instant at upper you know the other channels, if they are spaced one above the other, some other channels may actually give you some data, okay, which is also good for you. You can say that the height of the object, the height of the obstacle is limited to so and so, and then you can conclude that indeed it must be an obstacle. So, such interesting things can be done by just analyzing the data that is coming from the multi-line LiDAR systems. This indeed is a capsule on LiDAR. Our next task will be to actually show you a demonstration of how we can instrument this LiDAR, and a very simple application. It moves and then it finds an obstacle, it does something. We will have a look at that demonstration and then run through the code once to give you a feel of how it is actually the complete thing is programmed.